We now move on to explore the concept of concavity. And in order to do that, we need to move on to the second derivative. So, if we think about what the second derivative is, we know that it is the derivative of the first derivative. So that means that it is the rate at which the first derivative is changing, right? So just like if the first derivative is positive, then the function is increasing. If the second derivative is positive, then the first derivative must be increasing. Because the second derivative is the first derivative's derivative. And likewise, if the second derivative is negative, then the first derivative is decreasing. Okay? So the question now becomes, what does that mean for the original function? If our first derivative, or our slope, is increasing, then what's happening to f prime, or f of x, the original function? Well, we have a name for that. It has to do with the concavity. We call this concave up. And if we want to try to remember what that looks like, we think about the U, which is the first letter in the word up. Everywhere on this up is, everywhere on this U is concave up. Think about what the slope is doing. The slope is negative like 10 or something. And then the slope is negative 1. Okay, our slope changed from negative 10 to negative 1. Negative 10 equals our slope. Negative 1 equals our slope. Our slope equals 0 here. Our slope equals 1 here. Our slope equals 10 here. What's our slope doing? It's getting bigger and bigger, right? From negative 10 to negative 1, it's getting bigger. From negative 1 to 0, it's getting bigger, etc. So as our slope is increasing, we call our function concave up. And then you guessed it, if our second derivative is negative, our first derivative is decreasing, our original function is concave sideways. No, down. And we think about the letter N in down, or the upside down U. Same idea. We've got a slope that's very steep. Maybe the slope equals 10 here. I don't know. And then the slope equals 1 here, and then the slope equals maybe 0 here, and over here the slope might equal negative 1, and down here the slope might equal, say, negative 10 or something. And as we progress from a very large slope down to 0, down to negative slopes, that's a concave down graph. So right side up U is concave up, upside down U is concave down. The down makes a frown. So remember that f prime of x measures the slope of the function, and as the slope changes, we are changing the direction that we're heading. All right, so here's kind of a summary. We can describe each slope. What did I just do? Oh, no. I didn't want that. So we can maybe describe each slope and how it's changing. So first of all, the slope is positive here, and the slope is positive here, and the slope is positive here, right? Because for each one of these on the left side, our graph is increasing, right? Over here, the opposite is true. All of these are decreasing, so f prime of x is negative here, f prime of x is negative here, and f prime of x is negative here. All right, talk about the second derivative. Our second derivative, well, this is getting steeper and steeper and steeper in the positive direction. So this is f double prime of x is positive. This is f double prime of x is, I wonder. What do you think? What's the slope here compared to here, compared to here, compared to here? The slope is the same everywhere because it's a line. So our slope is not changing. So that must mean our second derivative is equal to 0 because f prime is not changing. It is constant. And then finally, our slope gets steep, and then less steep, and less steep, and less steep is getting closer to 0 from the positive end of things. So say negative, or positive 10 to positive 1 to positive 1/2 or whatever. So f double prime of x is negative because f prime is getting smaller. F prime is positive, but getting smaller. And then kind of the same idea over here. F double prime of x is positive because we go from a negative value that's far away from 0 to a negative value that's closer to 0. 0 is the big number when we're talking about slopes over here. Again, with that constant slope on a linear function, f double prime of x is equal to 0 because f prime of x is constant because the slope of a line is constant because that's what lines are, things that don't change direction. And finally, f double prime of x is negative here because we start at a negative slope that's close-ish to 0 to a negative slope that's far away from 0. So these two on the bottom are concave down. They're making the frown of this sad person. The eyebrows up here are making the concave up part of it. So last section, when we talked about the first derivative test, we saw that there were special places where the first derivative changes signs, and the first derivative test told us that when the first derivative changes signs on a continuous function, we have a relative extremum. Relative max or min. Another important point is the second derivative changing signs. This is called a point of inflection. Okay. I like to think about driving down the road with points of inflection. If we're curving one direction, we're curving to the right, our steering wheel is turning to the right, and then we start turning to the left. That point where our steering wheel stops turning right and starts turning left, that is a point of inflection. We change our concavity, in this case from concave down to concave up. Any change in concavity, any change in sign of the second derivative is going to be a point of inflection. All right, so that's another important characteristic of graphs that we're going to be asked to talk about. So remember that if f double prime of x is positive, and that tells us that f prime is increasing, which tells us that f of x is concave up. And if f double prime is negative, that means that f prime is decreasing, which means that our function is concave down.